All right. The impulse train. Yeah, okay. So impulses we talked about last time. Impulse, basically, what does it model? I mean, what is it representing physically? It's a weird thing. It's an arrow that points up or an arrow that points down, which is a purely mathematical thing. But what does an impulse represent?
Wasn't it the confusion that would come from like flipping a switch in a circuit, so you effectively, but not really, go from 0 to some value instantly, but you couldn't really model that, and so the impulse is that?
Yes, that's sort of correct. It's essentially a situation where I have a really big change that happens, and it's modeling that really big change. So the example that I sort of gave to that was, I said the impulse is by definition the derivative of the unit step. Okay, and so you look at this picture here. You look at the picture on the left. This picture here shows the way that things would really happen in the real world typically, right? Over a short time t here, this guy is ramping up, right? So what I'm looking at is the derivative, which if you think about what's the height of that guy going to be, well, if this time is really short, then the height's going to be really big, right? It's just a slope, right? Rise over run, right? He rises 1, but his run is a super small number, so is a really big number. Okay. And so if you look at this picture here, you see he's got, so this change happens over a time t. So the derivative here would be a constant over that time t with a height 1 over t. So what's the area under this curve right here? 1. Yeah, this area is 1. And the impulse basically takes that to the limit to say the limit as t goes to 0, right? What I get is this arrow guy, all right? Now, that height value is actually the area, right? Not the actual height. So that's the thing I would point out with this guy. So when I write a number here, it doesn't mean its height is 1, okay? So when you do problem 4 and you're plotting the actual pulse train that I gave you, you're going to see the heights get very big and the pulses get very skinny, all right? So they're tall and skinny. Their area is 1, okay? All right, so it's by definition the derivative of the unit step. Okay, now, and its area is 1. So in other words, it is delta of t dt, negative infinity to positive infinity is 1. All right, that was an important fact. The other important fact I gave was that it has this thing called the sifting property, right? The sifting property basically says that if I multiply a function by a impulse, then I integrate over the interval at which this impulse appears, then what I do is I pick off the value of the function at that point. All right, I basically sample the value of the function at that point. All right, so I gave this picture here. So here's f of t, and here's an impulse located at time t, which importantly I say is written as delta of t minus capital T. All right, so at that point, then what I do is I pick off the value of f of t at that point, which is going to be the value f capital T. Okay, so what I wanted to do is I wanted to use that here for my impulse train. All right, and we did a little bit of that last time, but I wanted to review this here real quick. Okay, so in problem 4, right, what you have is you're figuring out the Fourier series coefficients for this impulse train. Okay, and what I have is basically alternating impulses up and impulses down with the same area of 2. Okay, so I gave 4 steps basically for figuring out what the Fourier series coefficients are. Right, so the first step is we figure out the fundamental period, which we figured out last time was 2. Okay. The next step is I needed to be able to figure out a function, all right, for x of t over a period. Okay. So in this particular case, I have x of t equals 2 delta of t minus 2 of delta t minus 1. So that's basically including this pulse here and this pulse here. Okay. And then what I did was I integrated, this was a tricky integration because I can't start at time t equal to 0 and end at time t equal to 2. Why can't I do that? What's the problem with starting at t equal to 0 and ending at t equal to 2? That's a period, right? What's wrong with that?
It's ambiguous.
It's ambiguous, and we don't like ambiguity, right? So we want to start at something it's ambiguous because it's basically the impulses are located at 0 and 2, and that makes it confusing, right? So what I did was I backed it up a quarter of a period, all right? And that still includes 2 impulses, okay? And the nice thing about it, let's take a look here at my alpha n integral that I've got written right here. Okay, so I set it up basically using what I wrote right above it. And then I used that sifting property. And that's the thing I wanted to talk about real quick, right? So what I have is 2 delta of t times e to the negative j n omega naught t minus 2 delta t minus 1 times e to the negative j n omega naught t, right? That basically looks like, to me, I have an impulse times a function f of t, right? That's what's written out there. The function f of t in this case is that e to the negative j n omega naught t, right? So what do I do? When I take the integral of 2 delta t times e to the negative j n omega naught t dt from negative 1/2 to 3/2, what's that going to be equal to? Is that a hard integral to do? No, it's a very easy integral. What's the value of it? What's the value of that guy going to be?
Isn't it going to be like 2e to the negative j n omega t?
Yep, 2e to the negative j n omega naught times 0. All right, because what we did is basically, if I look at this, what I have here is, this looks like to me delta of t times f of t dt. So it just pulls off the value of that function at time t equal to 0. And the value of that function at time t equal to 0 is 2e to the negative j n omega naught times 0, or just simply 2. Okay? Questions about that? All right. So that basically, that simplifies your calculus a lot, right? So if you looked at what I did here last time, right, it meant that for the first impulse here, I pulled off the value of f of t at t equal to 0. And for the second impulse, I pulled it off at t equal to 1. Okay. And that gave me this result here, which we said your result's always going to be a function of n. All right. It's always going to be a function of n. Because again, we can easily get lost in the math here, right? But remember, what is the physical meaning of alpha n? What is alpha n? Let's just not lose. This gets a blur of j's and deltas and Greek crap, right? What is this? What is alpha n? What is it in the real world? What does it mean? Yeah. Anybody online? Take a stab at that. What the heck is alpha n? Let's not lose sight of what it means. You guys are quiet. That worries me. Either you're not paying attention or you don't know, or you're shy.
Is it the peak of the graph, maybe?
The peak of the graph. What graph are you talking about?
Yeah, that was my guess. I fulfilled my quest.
Okay. Anybody else?
I actually had to go use the restroom real quick. What was the question again?
What is alpha n? What is it?
Ooh.
So once I've done this, what is it? So when I figure out the alpha n values, what the hell have I figured out at the end of the day?
Isn't it some?
It's the average value of the waveform, right?
I'm glad I asked this question. It could be the average value of the waveform in certain cases, right? What is alpha n? Philip figured it out here in the room, but I want to hear somebody else online.
Is it the location of each one of the impulses on the t vector?
Nope. So the location, so we've got here that the location of these impulses, I got them at 0, 1, 2, 3, 4, 5, 6. Basically, remember, so let me go all the way down to the bottom of my slides here. What we said is that this function, any function, can be represented as this summation. Okay. What for a function to be represented by this summation, what did it have to be? What it had to be true about this function for this series to be true?
It was a waveform, so it's like either cosine or sine, right?
Well, no, I mean, so you got the right idea, right? F of t, for this
and can't be
summation to
zero?
be true, right? What does the function have to be? It has to be a waveform of some sort. It has to be periodic,
Oh.
right? For a function to be represented by a Fourier series, the waveform has to be periodic, okay? And what this, so if I see you on the street 10 years from now, you're not going to remember how to calculate alpha n. You probably won't even remember that you ever learned alpha n, okay? But if I ask you what a Fourier series is, tell me in words what a Fourier series is.
Isn't it just a sum of waves that, when put together, can create a non-continuous but periodic function? So like a function that's either on or off, then we, yeah.
That's right. If I have a periodic function like a square wave, okay, so if I had a square wave going up and down, or like the stuff you've got in the homework where I've got it going up and like this, right? Those are both periodic functions, okay? Both of which are pretty common in engineering problems, okay? And, you know, this guy right here on the bottom is something I call a pulse width modulated waveform, right? So if you've done anything with robotics or whatever like that, this guy would be the kind of thing I would use to control the speed or the position of a motor, okay? That's a periodic waveform, okay? And it can be represented as a sum of sine waves or cosine waves, or alternatively, e to the j n omega naught t, okay? So then these alpha n values are what?
Would it be the amount of times the wave is repeated?
Or the
Would it be have that goes up and down?
Well,
Harmonic?
The magnitude of each wave that you're adding up.
That's right. It's the magnitude or the amplitude of each wave that goes in there. Okay. And so what that says, you know, in this case, the complex form of the series is the easiest to do the math with. All right. And you may not agree with me on that, but try doing problem 3 with the sine and cosine, right? You would hate doing problem 3 with the sine and cosine. You could do it, but it would suck. Okay. You doing it with the e to the j n omega naught t is easier. If I look at this, if I had a single sine wave, this guy would be alpha minus 1 e to the negative j omega naught t plus alpha 1 e to the j omega naught t, like that. This guy would be 2 magnitude alpha 1 cosine omega naught t plus whatever the angle of alpha 1 is, right? So if I had a single sine wave or single cosine wave, I could represent it as a vector moving in the complex plane in the negative direction and a vector moving in the complex plane in the positive direction. The alpha values tell me how much of each of those things I need to put in to create that waveform, okay? So like in problem 4, all right, you've got something like this guy, an impulse train. And what you are physically doing is you're saying, well, I need to add, if this guy has a period of t equal to 2, that means omega naught is pi. So you're basically, what you're saying is I need to add in some amount of 2 alpha 1 cosine pi t plus theta 1. And I need to add in some amount of 2 alpha 2 cosine 2 pi t plus theta 2. All right. And what you're doing is you're figuring out, well, how much of each of these things do I need to add in to make that summation look exactly like this impulse train? All right. That's what's happening. All right. And so I wanted to say that because at the end of the day, whether you can do the math or not, I mean, Zach sent me his code yesterday. He had MATLAB doing the integrals for him. Good for him, right? At the end of the day, your boss is never going to ask you to take an integral, but you probably will need to have some understanding of what a Fourier series is. All right, so I say that don't lose sight of the bigger picture sometimes. You guys are obviously very worried about the questions I'm going to ask you to get the points that you need, right? And that's always going to be integrals and things. But what a Fourier series is the important thing, okay? It basically says that any periodic waveform can be represented as a sum of sine waves. And these alpha values are the amplitudes, okay, of those sine waves. So we're basically figuring out the specific amplitudes that go into the waveform. Now, Zach, you said, well, this is the DC value. In what special case, Zach, I'll call you out on this, right? In which special case does alpha n give me the DC value of the waveform?
Alpha 0.
Alpha 0, right? If n was equal to 0, then I'd be taking the average value of the waveform. Okay. All right. Any questions about that? Because again, to me, that's an important concept to have. All right. All right. So real quick, I'm going to throw in, so one thing I should probably mention here, that impulse, right? We talked about things as a function of time. There's no reason why I couldn't have an impulse that was also just had in other words, I could have a delta of x, right? And I could draw that guy on an axis that was labeled with an x, okay? Delta of x would sit there. If I had delta of omega, that's fine too. It just means that my x value, my x-axis value would be omega, okay? Because what I want to do is I want to use this delta concept with a frequency variable, okay, rather than with a time variable. You can use it with whatever independent axis variable you want, right? I'm going to use it with omega, all right, in the next part of this. Okay. Questions about that? Okay. All right. Let me move on then. So if I'm looking at this picture right here, we talked about this last time. All right. I said, here's an x of t. Here's a signal that was measured in the real world using an app on my phone, which means that essentially what I have here is it's a periodic waveform, although you don't see the periodicity per se. It is periodic. And I'm looking at part of the waveform here. All right. Now, effectively, what's happening here is this is on my phone. So basically, what's happening is the sound wave hits the microphone, and the microphone basically converts the vibration that comes from my voice into a voltage. Okay, and that voltage can get processed. So this signal here contains different frequencies, and those frequencies are representative of my voice and the way that my voice speaks certain words. So, I talk about this because the question is, well, what do you use any of this Fourier stuff for? Well, what do you use it for? You say, well, if I have a periodic waveform, I want to be able to figure out what those alpha values are. I want to figure out probably what frequencies are in this waveform, right? What sinusoidal frequencies are in this waveform, and how big are those? How big is the signal at those frequencies? All right. That's what really, when I calculate the alpha ends, that's what I'm doing. I'm saying, what frequencies do I have, and how big are the signals at those frequencies? That's what the Fourier series analysis does, is it tells us that. And I could use that information. I could use those alpha n values, for instance. I could use those alpha n's that come out of doing this and put them into a voice recognition algorithm. right? By looking at the alpha ends and at what frequencies those alpha ends sit, that tells me something about what I might be saying. All right, and that's what a voice recognition algorithm would do, is it would try to process that stuff. So, you know, what I said last time is then what that means is if I'm looking at a picture like this, this is essentially versus frequency. What this is doing is it's telling me what signals are present in my waveform, all right, in my x of t. So what this is kind of saying to me then is it looks like so in this case, notice my x-axis is in frequency, in hertz. The y-axis here is the magnitude of the sine waves that I have, okay, at each of these frequencies. So wherever I have one of these spikes here, this guy kind of looks like a little impulse, right? He kind of looks like he's sort of just doing a quick jump up, okay? So what this says to me is, you know, I can see that one of the frequencies there looks like it's right around 412 hertz, okay, which is that number right there. That tells me that I've got something, you know, that has an amplitude alpha 4 cosine of 2 pi 412 t plus some angle. Okay, I don't really care about what the angle is typically. All right, but that's what this is telling me, right? Is I have something at this frequency and I have that much of that frequency there. Okay, that's what this thing is telling me. And so in this case, this is really similar to the Fourier series, right? The Fourier series basically said, well, I know what the fundamental frequency is. I know this guy has a frequency of 2 seconds. And so I know it has waveforms in it that are harmonics of that fundamental frequency. So let me ask you this. What does it mean to be a harmonic? What frequencies are in it? If this guy has a fundamental period of 2 seconds, what frequencies are present in that signal?
2 times some like constant, like some integer.
Yeah, so in this case, yeah, an integer, basically all the integer multiples of that fundamental period. So this guy had a period of t equals 2. That meant that the fundamental frequency was pi. So it's got something at pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi, etc. Right? All of the integer multiples of that fundamental frequency. Okay. Now, that meant that our alpha n values corresponded to n equal to 0, n equal to 1, n equal to 2, n equal to 3, right? So, and what I want to do is I want to basically look at a waveform and I want to be able to say at what frequencies do I have those alpha n values? And I want to plot them versus frequency, okay? I want to plot the amplitudes versus frequency. It's almost exactly the same thing as the Fourier series, right? The Fourier series just tells me the alpha n values. It tells me the amplitudes at the nth harmonic. Well, okay, that's fine. That's okay. I want to also know at what frequency they are. So this is a very trivial change what I'm doing. All right, I'm just trying to look at things a little bit differently, right? So if I have this waveform up above here, 3 cosine 2 pi t minus 30 degrees. What we said last time is I could use Euler's identity to make this jump here. Okay. All right. When I say I used Euler's identity, what did I do? What specifically did I use to make the jump from the left side to the right side? I said what? I said cosine of theta.
You just convert it to like the complex form pretty much.
Yeah, so how did I do that? Cosine of theta equals what?
1/2 times e to the j omega t time
Well,
plus e to the j 2 pi something or
yeah,
theta.
so cosine theta equals 1/2 e to the j theta plus 1/2 e to the minus j theta. Where in this case, theta must have been 2 pi t minus 30 degrees. Okay. In other words, the argument there is 2 pi t minus 30 degrees, and that leads me to this statement here. Okay, so I broke them apart. Basically, the two exponentials got broken apart. Do we have a network 2 test tomorrow? I thought there was a real question in the chat there. All right. All right.
Wait, that is a question.
Well, it is fair enough, but not a real question as far as I'm concerned. All right, so here the Euler's identity statement that I have right here. If I look at this guy right here, I want to be able to say, all right, at what frequencies does this signal have information? All right, of all the frequencies in the universe, at what frequencies does this particular signal here have information? Yeah. So somebody online, at what frequencies does that guy have stuff happening?
1.
Okay, one with what units?
Hertz.
Hertz. Okay, at what radian per second frequencies do we have?
2 pi.
2 pi, and at negative 2 pi. If I want to do it in the complex form, I've got it at negative 2 pi. Okay, so what I'm going to do is I want to sort of look at this guy as in some way, and I want to say, you know what, I'm going to write it like this. I'm going to say, I want to represent as a function of omega where this guy has information. Okay, so what I'm going to say is I'm going to write it like this. I'm going to say 3/2 e to the minus j 30 degrees times delta omega minus 2 pi plus 3/2 e to the j 30 degrees times delta omega plus 2 pi. Okay. What does that mean? Let me try something simpler for a second. Let's say I had x of t equals 3, just the number 3. Okay. If I had x of t equals 3, at what frequency does this guy have information?
All of them?
No. At what frequency does that guy have information? Is he varying at all? If I have x is equal to a constant, is there any variation in that number?
No.
No. So what frequency is that?
0?
0. DC, right? So what that says is I'm going to try to express this guy as in a world I call the frequency domain. And I'm going to say that he has energy only at 0. So I'm going to express that as 3 times delta of omega. Okay. In other words, there's only energy at 0 radians per second or 0 hertz. Okay. Only at those frequencies. If I gave you instead, let me take a simpler one. X of t equals 3 cosine t. Okay. At what frequencies does x of t equal to 3 cosine t? At what frequencies does that guy have energy? Somebody other than Zach.
Everything except like multiples of pi over 2.
So 3 cosine t. You got the right idea, right? But 3 cosine t, what's the frequency of that signal? 3 cosine t, what's its frequency in radians per second?
1 over 2 pi?
What's its frequency in radians per second? You were close.
2 pi, right?
In radians per second.
Oh, wait.
Like 90 or 0 to 360 something.
What's the frequency of 3 cosine t in radians per second?
Is that one?
Wouldn't it be 1?
1 radian per second. right? It's cosine omega t. The frequency of that guy is 1 radian per second. Okay. So the only frequency in radians per second at which he has energy is 1 radian per second. Okay. So I want to say I'm going to express this guy as having half of his energy at 1 radian per second and half of it at -1 radian per second. All right. In other words, what I'm trying to say is if I use Euler's identity, I can use Euler's identity to break up this cosine into 2 complex exponentials, one moving forward and one moving backward. And then what I can do is I can say, well, the only places where he has energy, and I'm using this kind of loose term, I'm basically saying the only frequency at which anything is happening in this signal is omega equal to 1, right? And if I write it in terms of Euler's identity, it means I have something in omega equal to 1 and an omega equal to -1, right? So the idea here is, all right, the idea here is that what I'm looking for is there's going to be, it's called the Fourier Transform, okay? What it says is the Fourier Transform tells us the frequencies at which our signal has energy. And if I have a periodic signal, the frequencies where that happens are the harmonics of the fundamental, okay? So in other words, at n omega naught, okay? So, and the values specifically are the alpha n values, all right? So we got to unpack what that means here a little bit. So let's take a look at this signal right here. X of t equals 4 cosine 2 pi 60t plus 60 degrees plus 6 sine 2 pi 180t, like that. Okay. All right. So before we go too far with this, and let me make 2 places for me to work. Okay. All right. Before I get too far with this, since there seemed to be some confusion there for a second, let's look at X of t. At what frequencies are present in that signal? All right, so X of t, what frequencies are there? What omega values do we have in that signal, X of t?
Two pi 60 and 2 pi 180.
Those are two of them.
And 1.
Yep. Not 1.
0.
0.
0.
Okay. 0. All right. Those are the frequencies that are clearly present in that waveform. What's the fundamental frequency?
2 pi 60.
2 pi 60, right? So if I look at my n values, that means this is my fundamental here. This is n equal to 0. What about 2 pi 180? What's that one? What n value does that correspond to?
2, right?
3.
3.
Oh, 3. Yeah.
Right? So this guy looks like he's got n equals 0, n equal to 1, n equal to 3. Okay. All right. I want to express this thing in the frequency domain. In other words, I want to say at what frequencies, I want to draw a graph that basically tells me at what frequencies does this signal possess information. Okay. And I know right now that where it possesses information is at DC, 2 pi 60, and 2 pi 180. The thing I want to do is I want to say, well, how much does it have? Well, that depends on the amplitude. Okay. So let's look at this guy right here. So basically what I'm going to do is I'm going to write this X of, before I even try to write out that X of j omega thing. X of t. Let's write that in terms of Euler's identity. Right? Because I want to write this in the form of the complex form of the Fourier series. Okay. So X of t equals 5. Right? I don't do anything with 5. It's a constant, right? Right, but 4 cosine 2 pi 60t plus 60 degrees. What do I do with that? How do I get that into the complex form of the series? What do I do to get that into complex form? Well, I got to use Euler's identity, right? So how do I do that?
So you multiply it by, oh, so it'll be 2 cosine e to the j or 2e to the j 60
Yep.
e to the 2 pi 60
With a J in front.
j 2 pi 60 plus e to the negative j 60.
With a 2 in
Yeah,
front.
yeah, 1/2
Times.
e to the negative j 2 pi 60.
Okay. All right. Now there's also something I gotta do. I gotta do something with the 6 sign as well. But let's just stop there for a second. Right? Because what I want to do is I want to map just this right now into where are the frequencies at which this guy has information. All right. So the first one here, what frequency is 5?
0.
Yeah. So I'm going to write that as 5 delta omega. There's information at delta omega. Okay. So delta omega, what would that look like? Right? If I drew that on a set of axes, here's omega. Where would delta omega be?
Be the x-axis.
Omega is the x-axis, right? So where would delta of omega be? It'd be one of those little arrows, right? Where would that arrow be located? Where would that arrow be located? At what value of omega? 0, right? It'd be a right here, right? It'd be a pulse upward right there at omega equal to 0. All right, so let's keep going with that. All right, so this next one here, what's the only frequency represented there? So 4/2 is a number, it's 2. E to the j 60 is a complex number, right? E to the j 2 pi 60t is something that has a frequency, right? So what frequency is that guy at? What frequency is that at?
60 hertz.
60 hertz, or yeah, or 2 pi 60 radians per second, right? The way I'm going to write that is I'm going to say, well, that means I have this amount of stuff, 4/2 e to the j 60 at omega minus 2 pi 60 radians per second. Okay, so I guess the way I would write that is, well, let's stick with that for a second, right? I have basically this amount of stuff, 4/2. This is my alpha value, located at a frequency omega equal to 2 pi 60. Okay. Now, what would I do with this last one here? This last term. What frequency is that guy located at?
180 radians per second. You'd want to convert it to cosine, wouldn't you?
No, this one right here that I'm underlining.
Oh, sorry.
Yeah. What frequency is that guy?
Radian.
Yeah, what radian frequency is he at?
Negative.
Negative 2 pi 60.
Negative 2 pi 60. So in terms of the way I would write this guy, I would say 4/2 e to the negative j 60 degrees times delta of omega plus 2 pi 60 degrees, like that. Okay. All right. Now, before I move on to this, I want to say, well, what I want to do is I want to make a plot that looks kind of like this one right here. All right. I want to make a plot like this guy that basically shows, well, at what frequencies, and it doesn't matter. I can do it versus f. I can do it versus omega, right? I can do them versus whatever I want, right? I want to make that similar kind of plot. How would I plot this thing right here? This x of j omega. How would I plot that guy? In other words, I want to plot it versus frequency. Okay. How would I draw that plot? It looks like what? It's definitely a bunch of impulses, but they're weird because those impulses have basically complex numbers multiplying them, right? So I have 4 over 2 e to the j 60 degrees multiplying an impulse. All right, so weird just got weirder, right? So what do I have here? So what I have is something that I would call, I have a complex function, okay? A complex function. So a complex function is basically is a thing, or a function that is taking in, what we say, a real valued argument, in this case, omega, and it's basically creating a complex output, all right? In other words, I'm putting omega into this function, but this function gives me a complex number. I can't plot that very easily, right? But what I can do is I can plot versus omega. I can plot what the magnitude does, and I can plot what the frequency does. All right, I can draw 2 different graphs to express this thing. Okay, so let's just look at this for a second. Let's say I had what I wrote here, right? H of j omega is 4 e to the j 60 times delta of omega minus 2 pi 60. Okay, that's a complex function. All right, in other words, it's the variable here is omega. And I want to plot this thing, but I can't plot it easily, right? I can't plot a complex number. In other words, like I can't plot, here's omega, right? I can't plot h of omega, right? Because what's implied when I draw a graph like this, what has to be true about both? If this guy's a real number here, what does h of omega have to be? Have you ever seen somebody make a graph that has a complex y? Can you have a complex number like that? No, you can't do that.
Isn't that the complex plane?
Mm-mm. Let me ask you this. So if I have the complex plane, right? The complex plane says if I have h of omega, and that's a complex number, a plus jb, if I say this is the real axis and this is the imaginary axis, then I can draw a vector, right? It has a certain, but if I wanted to plot versus omega, if h is a function of omega and I want to plot it that way, right? This is like plotting, if I said here's the t axis, right? And I want to plot x of t. T is always a real number. Can I plot an x of t that's complex? No.
Why don't you just take the real?
Well, I could take the real part, I could take the imaginary part, I could take the magnitude, I could take the angle, but I can't do them all at once.
Could you do like a 3-dimensional graph?
I could make some kind of a 3-dimensional graph of some sort. Yeah, I could do that, right? That's not typically what we do, though. What we typically would do is we say, okay, well, let's try this. I've got basically 2 choices, right? One choice would be to say, well, I want to plot the magnitude of h of omega, or I want to plot the angle of h of omega. The magnitude and the angle are both real things. I can plot real versus real, right? But I can't have a real argument lead to something that I can visualize in 1 dimension, because there are 2 numbers that represent h of omega, an angle and a magnitude, or a real part and an imaginary part. So I basically have to draw those 2 things separately. Okay. Alex, you had a question? Or? I was going to say a comment about 3D. Oh, you potentially do a 3D plot of some sort, right? But typically we look at these as sort of separate graphs, right? We can look at, we need to look at 2 real numbers separately, right? We can't visualize the 2 parts of a complex number separately unless we could draw a 3D graph somehow, okay? So if I asked you, okay, well, what I want to do is I want to make a graph down here of the magnitude of h of omega versus omega, like that. All right, I want to draw that. How do I do it? What would that look like in this case? So I've got 4 times e to the j 60 degrees with delta of omega minus 2 pi 60. So first of all, this guy's going to be an impulse, right?
So you'd start at the frequency of negative 2 pi 60.
Yep. Well,
And then,
so not at negative 2 pi 60, right?
oh,
But
sorry, 2 pi 60.
2 pi 60, right? So 2 pi 60, there's going to be an impulse there
Yeah, and then the magnitude of 4.
and a magnitude of 4. All right, like that. What about the angle? What would that be?
Well, if you were doing the angle,
Oh, 2 pi 60 hertz or 2 pi 60 radians per second.
wouldn't it just be 60? Oh,
There'd be an impulse here that would be 60 degrees, like that. All right. So what it does is it expresses for me, right, that I have a magnitude of 4 at this frequency and an angle of 60 degrees at this frequency. All right. Now this is a weird function, but I could also have something like this. I could have h of omega equal to 1 over j omega plus 10. That's a possibility too. All right. Now that would be a different kind of function to look at. This is a pretty common one. All right. Chances are you guys have seen stuff like this with Yahoo in circuits too. All right. Chances are you've seen stuff like that. If you haven't, you will. Okay. We're going to talk more about this starting next week. Okay. But for today, I wanted to start with something which is hopefully a little bit simpler. Okay. So what I want to do is I want to use this fact and I want to go up to what the example I started with, right? So let's forget the 6 sine 2 pi 180t for a second. Let's forget that. All right. And so what we did was, let me make a copy of that. I'm going to forget this for a second. Make things a little bit simpler to begin with. Oops. All right. So I start with that. Now what we said on the previous slide here is I got to x of j omega is 5 delta omega plus 4 halves e to the j 60 degrees times e to the j 2 pi 60t plus 4 over 2 e to the minus j 60 degrees times e to the negative j 2 pi 60t. Okay, like that. Now, oops, that's not what sorry. That's what x of t was, right? This guy was at omega minus 2 pi 60. And this guy is the other place, like that. Okay. All right. So what I want to do is I want to plot x of omega, the magnitude, and I want to plot the angle here, x of omega. Okay. So how would I do that?
start on the magnitude of 0 would be 5.
Yeah, at 0, I would have, so if I do the magnitude, I'd have a magnitude of 5 here, right? So I would draw it like this. I have a magnitude of 5, like that. Okay. What about, what else would I have there?
You'd go to 2 pi 60 and then the magnitude of 2.
Yeah, to 2 pi 60 here, I'd have a magnitude of 2. And I would also have a magnitude of 2 over at negative 2 pi. Okay. Now what about the angles? What would my angle be here? What would the angle, my angle look like?
So at the 0, it would just be There's no magnitude, there's no angle for 0.
No angle, right? So I've got angles. I've got basically an angle of 60 and an angle of negative 60, right? At what frequency do I have an angle of 60?
2 pi 60.
2 pi 60, right? So there's 60 degrees right here. This is at 2 pi 60.
And the negative 2 pi 60.
At negative 2 pi 60, I have negative 60 degrees down at this frequency. All right, so basically what I've done is I've represented sort of the same thing that I was trying to show that this frequency analyzer does on my phone, right? It's basically, if I look at what this guy's telling me, it's basically like I've got these impulses at the frequencies where there is a sinusoid present in the waveform, right? So there was a sinusoid at 412 radians per second. Well, this tells me that in this particular signal, right? In this particular signal, there's something at 2 pi 60, right? And what I do is we do it in the terms of the complex form of the series. So basically what I do is I plot the magnitudes and the angles at those points, okay? All right, the magnitudes and the angles at those points. Now, if I included additional terms, like if I had the 6 sine 2 pi 180t, okay? Let me ask this, before we do anything with it, at what frequencies does that mean that I've introduced impulses now? What frequencies? What frequencies in radians per second? Somebody other than Tony there.
2 pi 60 and 2 pi 180.
Yeah, well, so yeah, there's stuff at 2 pi 180 and also in the complex form, also not just at 2 pi 180, but where else?
Negative 2 pi 180.
Negative 2 pi 180, right? So this guy, you know, there's a sinusoidal form of Euler's identity that you can use, right? But the way that I look at this is I say, well, if I have 6 sine 2 pi 180, that's the same as 6 cosine 2 pi 180 minus 90 degrees, right? And then what I would do is I would utilize then Euler's identity to say that makes this guy 6 over 2 e to the negative j 90 degrees times e to the j 2 pi 180t plus 6 over 2 e to the j 90 times e to the negative j 2 pi 180t. Okay, so if I wanted to add that to my graph, right, that means that at 2 pi 180, I would add a magnitude of 3. Okay. What do I add at 2 pi minus 180? What's the magnitude there? So this guy tells me I've got a term at minus 2 pi 180. What's the magnitude at that term?
Also 3.
Also 3, right? Nothing too fancy about it. Okay, this guy is 3. What about the angles here? What's the angle at 2 pi 180?
Negative 90.
It's negative 90, right? I got that negative sign right there. Maybe not too big. It's negative 90. So I would have at 2 pi 180, I'd have a negative 90. All right, and what about at negative 2 pi 180?
90 degrees.
90 degrees. Okay, I'd have a 90 degrees. So that'd be over here somewhere. 90 degrees at negative 2 pi 180. Okay, now this is just a different way of visualizing it, but it's basically the same thing I said, you know, that I had here on my phone that I might use for that kind of voice recognition problem. All right, this information is useful to me, and we're going to use it to be able to think about things like filters, right? Which is a pretty common type of problem that you have to do in engineering. Is I have to filter signals, and I want to remove certain sinusoids from a signal. Okay. I want to make a signal look a particular way. That's what a filter does. And we need this concept to be able to understand that really, really important idea. Okay. So if I wanted to plot this in MATLAB, okay, at this point I want to say, well, let's say I wanted to make a graph of something like that. So in this case, we just drew by hand right here what that graph should look like, right? So we drew the magnitudes and then we drew the angles, okay? Well, let's say I wanted MATLAB to do that. In other words, let's look at the graph I ultimately had MATLAB create, okay? So here's the graph I had MATLAB create. What it has on the top is the magnitude, and it tells me that I have a magnitude of 5 at 0 radians per second. I got a magnitude of 2 here. Now notice I put this in radians per second. So this guy is 2 pi 60. MATLAB's put a number for that, 377. All right, and then this guy here is 2 pi 180, which if you put a number in for that, it's like 1100 or something like that, radians per second. And you see the magnitudes match what I said they were, okay? And the angles are shown down here as well. All right, now, some of you guys that were in office hours last night were asking me this question. I said, well, what's that command you're using? The command I use to generate this is something called stem, right? What it's doing is it's basically drawing a little dot on top of a stem. That's why they call it that, right? Basically, it's my way of trying to draw impulses, all right? And so if I look here, here's the code that I used, okay? What I did was I created an alpha vector, right? And I created certain entries in that alpha vector. Now I did this from, it looks like, so I created an omega vector that goes from -7 omega naught up to 7 omega naught. So the frequencies that are in here are -7 times 2 pi 60, -6 times 2 pi 60, -5 times 2 pi 60. And I continued that all the way to 5 times 2 pi 60, to 6 times 2 pi 60, to 7 times 2 pi 60, okay? And what I did was I filled in those points at which I actually have something happening, all right? So then what I did was I used this stem plot here to basically plot the magnitude, and then down here to plot the angle. All right, now there's a couple of things going on in my code here. The other thing that I have, something I haven't asked you guys to use before, but I will probably start asking you to use now, which is this thing called subplot. All right, what subplot does, I'm not going to talk about the syntax of it here. I'll talk about that maybe a little bit next time. What subplot does, and I probably would only ever ask you to make a subplot with 2 plots in it, which is it basically puts 2 plots in the same figure. One on, well, you can, at least the way I've called it here, it puts 2 in the same figure. You can put 100 in the same figure if you wanted to. So in other words, if I looked in MATLAB, this would be one figure window right here, right? And I do this with these complex functions a lot, where I have a magnitude on the top one and then the angle on the bottom. So they notice that they have the same x-axis range. But I want to be able to see, well, at a given frequency, what's the magnitude and what's the angle, right? So I could put them together and get the full complex number, okay? That's sort of the basic idea here. All right, now, I will ask you to look at this in homework 8, okay? This concept is the last concept that will appear for exam 3, all right? This idea of the Fourier transform. On exam 3, I'm going to expect you to know the Fourier series and the Fourier transform. The Fourier transform gets more complicated than everything we've just talked about here, right? But we're not going to get more complicated than that. Now on Tuesday, I'll look at another example of this, but there are more complicated things that you can do. All right. For example, all right, let's say I have a square wave. Okay. So we've done this before, right? This was actually where I started out with, right? So if I figured out, if I figured out the Fourier series coefficients of the square wave, right? What I would get is that I get something that looks like this, all right? I get things at these frequencies here. So I get something at -5 times the fundamental, something at -3 times the fundamental, something at -1 times the fundamental, something at 1, 3, 5, and technically there's more, right? There's infinitely many of these things that add up to create that guy. But what I do is I can see the Fourier transform basically takes out these amplitudes of these different sinusoids that are inside of that waveform, and it plots them for me, right? But I do this as a magnitude and an angle, all right? So the magnitude here, all right, I basically plotted stuff at -5, -3, minus omega, and at omega, 3 omega, and 5 omega, okay? And then I did the same for the angles. So let's just take a look for a second. So if you look at this guy here, -2 over J5, right? -J over 2,5, all right? Sorry, -2 over J5. Yeah, so if you look at that, what's the magnitude of -2 over J5? What's the magnitude of that? Well, 5 pi. -2 over J5 pi. What's the magnitude of that? -2 over J5 pi. What's the magnitude of that number? 2 over 5 pi. Why not? Why isn't the negative sign there? Magnitude is always positive, right? Magnitude is the absolute value. So if I have a -1, what angle is -1 always?
Be 0.
No. -1 is what? So think about where -1 would be in the complex plane.
-90.
-1's over that way in the complex plane. 180 or -180. All right. Where is where's J? The complex number J. Where does that sit in the complex plane? Well, that's up here, right? What's the angle of that?
9 degrees or -90 degrees.
It's 90 degrees or -270 degrees, right? If I had minus J is down here, that would be -90, okay? So in this case, if I have -1 over J like that, right? J is -1 over e to the J 90 degrees, right? So that means e to the J 180 degrees times 1 over e to the J 90 degrees. That's e to the J 180 times e to the negative J 90. That's the way I look at that, right? Is to say, if I have 1 over an exponential like that, it becomes e to the negative exponential. So this guy has e to the J 90 degrees. So at that frequency, at 5 omega naught, I have an angle of 90 degrees and a magnitude of 2 over 5 pi. All right, so if you track this, well, the next one here, what frequency is this guy at? Well, -3 omega naught. So at -3 omega naught, the magnitude is 2 over 3 pi, a little bit bigger. What's the angle at this particular frequency? What's the angle there? Isn't it going to be the same? Still 90. Yep, still 90. Right? So when you look at this case, I'm going to get stuff that has, for all the negatives, I'm going to get angles of 90 and angles of -90. Okay? All right, so we got more to talk about on this, but I'm going to stop there for now. Okay? In the next homework, you'll be dealing a little bit more Fourier series. All right, but we're also going to start looking at this Fourier transform idea. Okay? All right, so I'm going to stop it there and stop the recording.